So, rotation of axes. Sometimes you might have a conic, a parabola or an ellipse or a hyperbola that doesn't line up nicely, nice and perpendicularly, so to speak, with the x and the y axis. And so we have a way of kind of creating a new set of axes that actually is in line with all the formulas and general forms for the equations that we have to make them easier to work with. So, to start this section, we're going to talk about the general form of conic sections. Before we do any completing the squares and setting them equal to 1 or anything like we've seen for hyperbolas and ellipses, or found out what the magical p number is for the parabolas, you can always write any of these things as an expression of just numbers being added together set equal to 0 with variables and coefficients. What makes them a conic section is that you have the x squareds and the y squareds, or a xy squared, this b in the middle. So it says provided a, b, and c are not all 0, so you can't not have all of these, not all 0. If you don't have, or if all of those are gone, what are you left with? Just a x to the first and y to the first, and you would have a line. And this isn't about lines, so we know how to deal with that already. So you need an x squared or a y squared or an xy term or any combination of those to get an ellipse, hyperbola, or circle. So if you put them into this format, just from the coefficients and their signs and things, we can tell what type of a conic we have. So if you have, let's first talk about ones that do not have an xy term, and that should seem good because we haven't done anything with an xy being multiplied together term yet so far. So it is going to be an ellipse if a and c are the same side, either both positive or both negative. So a and c being the x squared and the y squared. If they're the exact same, then you have a circle. For example, x squared plus y squared equals 1, the unit circle. This is precalculus, right? The a and c are 1 in this case, and they're both positive and they're equal, so it's definitely a circle. If they're not equal, then you have an ellipse. So if you have 1x squared plus 2y squared equals 1, or equals 0. I'm sorry, these are supposed to be equal to 0. I just used the equals 1 analogy because of the class. You could always push that 1 over to the other side, and then you'd have it equal to 0. I think the point was made, though, hopefully. Okay, so same sign, they're an ellipse, a and c, the squared term coefficients. If the squared term coefficients a and c have different signs, then you have a hyperbola, because we learned hyperbolas had the subtraction between the x squared and the y squared term. And the parabola only has one squared term. If you have x squared, well, that's what we're used to. Think of it as an example of what we're used to, y equals x squared. It's going to open vertically. It won't necessarily always open up. Maybe it opens down, but you can get that much information just from knowing that. And if you've got y squared, then it opens some flavor of horizontally. So there's always a table in every textbook here, and our text is no different. I tried to rewrite it to emphasize the actual meanings here, opposite signs, same sign, things like that, rather than greater than or less than or 0, because I think it's a little more clear this way. Okay, so let's just do an example and identify the type of conics that we have here. For our first one, we look at the x squared term coefficient and the y squared term coefficient, and they have opposite signs. And that tells us we have a hyperbola. We could then complete the square and put it into the form and do all the things we did, but that was back in the hyperbola section. We're just learning this new skill here. Okay, so what do we have for our second example? Looking at the square. We've only got one squared term, and that tells us that we have some type of a parabola. All right, so the next one, we look at the x squared and the y squared terms. They are the exact same. What do we know about when they're the exact same? Well, that means that if they have the same sign, they're an ellipse, but if they're the exact same, they're a special ellipse, they're a circle. Okay, let's look at these ones. The last one, looking at the x squared and y squared terms, again, they have the same sign like the last example, but they are different, and that's when we get not a circle but an ellipse. Okay, so far we've been talking about non-xy conics. What about xy conics? So if you've got an xy term present, it has the effect of taking a conic and rotating it about the origin by some angle theta. So we're looking at this and we're seeing, hey, that looks an awful lot like a ellipse, but it's definitely not in the format we're used to, having either a vertical major axis or a horizontal major axis. It looks like it has a 45-degree major axis, and we don't have any way to work for this. So I have this thing linked. Let's take a look at it quick. That might just be an image credit. Yep, just an image credit. Okay. All right. Back to the slides. We're going to just pause right here. No, we're not. All right, so now let's talk about rotation of axis. Informally, the idea is to use substitution to generate a new equation for our conic, which involves an xy term. To put that xy term having equation into a format that we're more familiar with, we're going to use a substitution which will generate a new set of axes, which we're going to call x primed or y primed. Almost every text that I've looked at with this uses their own notation. Sometimes it's a big bold capital X and a big bold capital Y, or an X with a hat and a Y with a hat. The meaning is what's important. It's that orange set of axes, which when you look at this ellipse, you're like, okay, now its major axis is in the x prime direction, and we could probably use all of our old formulas to talk about this thing. So that's the game. The question is, what is that substitution? And the substitution is this. And I see I've made an error because in my typing, I didn't get it all correct. That shouldn't be x hat. That should be x prime. So the substitution is everywhere you see an x in the original equation, these are the originals, the original x and the original y, you are going to replace it with the entire expression of x prime cosine theta, y minus y prime sine of theta for x, and the y guys get replaced with x prime sine of theta plus y prime cosine of theta. And what happens is under the substitution, you get a new equation for the conic in terms only of x prime and y prime now. And these coordinates will relate to our original conic as having that new rotated x prime y prime axes as shown in the picture on the prior page, where theta represents the angle that we started on our original xy axis and rotated to get these new x prime and y prime axis. There are some great I posted alternate readings about this in the reading assignment for this section, which do a really good job of having a look at this. So I encourage you to look at those as well. So the end idea informally is, you can think of it as, if we just treat the resulting equation in terms of x prime and y prime as the normal x, y, then we can graph the original rotated conic and the new equation for the conic treating x prime and y prime as our new normal x, y. You get a graph of our new conic using these x prime and y prime variables. But on our paper, what we'll have graphed will be standard oriented axis with, excuse me, I'm sorry about that, which will be oriented like we're used to. In other words, the axes will be parallel to the x and y axes as we're used to putting. So that's a bit. Let's just dive in and have an example of it. And so 2x squared minus xy plus 2y squared minus 30. None of those shortcut rules apply here. That's a lie. We have both positive. Yeah. Never mind. This is what happens when you turn out a whole bunch of videos in one afternoon. All right, I am going to stop this and start again.